Hey students, Thrasher here. We are looking at parallel circuits. Okay, we looked first at series circuits. We're just looking at another type, another way of wiring things together. So we're going to look at the definition, how they look, and a couple somewhat unintuitive properties that parallel circuits have. Before I get into parallel circuits, I want to go over some key ideas. And the first one is that voltage goes by many names. Sometimes it's referenced as potential, potential difference, electric potential, also EMF, electromotive force. In this class, if you come across any of these names, it's the same thing as voltage. Note though that voltage is not the same thing as electric potential energy. Voltage is defined as the change in energy per the amount of charge. Okay, so these things are not quite the same thing as electric potential energy. All of these are the same thing as V. Okay? Now, when we're talking about circuits in this class, we're always going to have a battery, and that is the only thing responsible for giving voltage to things. So it will make up the total voltage in our circuit, and due to really conservation of energy, as we discussed before, the charges have to give up. They have to use up any voltage that they acquired, that they gain from the battery. Batteries give voltage, and resistors, things like light bulbs, they will take away voltage. Okay? Well, all right, let's talk about parallel circuits. Okay? Components are said to be wired in parallel if there are multiple paths for the electrons to travel. So for series, it was always one path. If there are multiple paths, multiple choices, so to speak, for the charge, for the current to flow, well, then we say it's wired in parallel. Now, if I pick a spot on the wire, like right here, right at this spot, all the electrons have to flow through this spot. Okay? All the current, or the total current, flows through this location. But as that current is flowing, now there are three different branches. Not all the current will flow through this one. Some's going to take this path. Some might take the scenic route, I3. I'm just labeling these based on the resistors that are here. I3 is going through this resistor labeled, I1 is going through this resistor labeled 1, I2 going through resistor 2. You get the idea. So the current is going to split up, but eventually this whole area here, including this section, the current is meeting back up. I2 rejoins, I3 is going to keep on flowing and meet up here, and that's going to meet up with I1. I again have the total current at this spot. So current can split up, but no, there are places where it all meets back up. Imagine a racetrack, and you had three different paths. Well, when all those paths come back together, all those cars in the race must rejoin. So we have a slightly different setup for current in parallel. The total current is just going to be all the individual branches added up together. If there's 2 branches, you add up the 2. If there's 20 branches, you add up all 20. All right, so that's it for current. Let's look at the voltage. When the electrons complete one path, remember, they must use up the voltage given to them from the battery. Start with this example to kind of prove it to ourselves. I have 2 people holding 2 balls. Each one is a certain height up, and they're the same height. Ooh, tough to draw a straight line. Both of these objects have the same gravitational potential energy. There's 2 different ways for me to drop this ball. I could either drop it on the left, drop it on the right. Just like the electrons have 2 different paths to flow. Well, the Earth doesn't care. The Earth doesn't say like, oh, hold on, wait a second. We first have to deal with the one on the left. The Earth will pull on both of them equally. There's both 2 direct paths from the air to the ground, 2 direct paths. Well, likewise, there are 3, in this case, direct paths to the battery. Here's a direct path. Here's another direct path to the battery. Here's a third direct path to the battery. So the Earth gives the same gravitational potential energy, And similarly, there's the same amount of electric potential energy and therefore the same amount of voltage given to each parallel branch. So, unlike in series circuits, what's key is this spot here. The total voltage goes to each of those branches. Another way to think about it, remember, the current could take this path, this inner one. Well, if this is a 9-volt battery, the battery gives charges 9 volts, 9 joules of electric potential energy. This resistor must take 9 volts. If the charges took this middle path, the battery is giving 9 volts. Well, in this case, they're going through this resistor. It must use up 9 volts. If they take the outer path, let's see, can I get another color here? Blue. Well, the battery is giving 9 volts. This resistor must take 9 volts because it has to take the voltage that is being given. So all branches get the same amount of volts. Okay, well, let's do some math. We just did this on the last slide. The voltage is the same. We saw a slide previous, this, that the currents add up across all those branches. Well, using this and Ohm's law, we can figure out kind of the last piece of our puzzle, what's true about the resistance. I'm going to use this equation here. And instead of I total, I can plug in V total over R total. Oops, that should be a total. That's all I'm doing. Instead of IT, I'm going to put V divided by R, because I is V over R. So I total is V total over R total. I1 is V1 over R1. But wait a minute. V1 is V total. They're equal. So instead of writing V1, I'm just going to put V total. So here I1, that's the same as V over R, V total over R total. For I2, I could put V2 over R2. But, oh man, V2 is V total. So I can keep all the same V's up here. And I'm left with this expression. I'm going to get rid of this eraser mark. Well, I have this equation. If I just divided both sides by V total, all of a sudden all those V's are going to disappear. And I'm left with this equation. 1 over RT, 1 over the total resistance, 1 over R total. That's equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is actually an interesting equation because if I go to the next slide, if you do some math, if I have a basic circuit, I have a resistor of 2 ohms here, I have a resistor of 2 ohms here. 1 over R total, that's 1 over 2 plus 1 over 2. Well, that's just 1. And then you got to take the reciprocal. I don't want 1 over R total, I just want RT. Well, the reciprocal of 1 is still 1. But notice, the total resistance is less than the individual resistors. And the total resistance is less than these resistors just by themselves. Oh man, when things are wired in parallel, the total resistance goes down as you're adding more and more resistors. If I added a third resistor, you could do the math if you want, but this will get even smaller. That seems weird. In series circuits, the resistance added up, and that tends to make sense. Here in parallel, adding resistors makes it smaller. And while at first glance that seems weird, in reality, that actually should make perfect sense. And in order to show that, I'm going to use a toll booth, a toll road analogy. Imagine this is like the Golden Gate Bridge. Here's a toll booth. This on the far left would be a pretty poor design because all the lanes of traffic on the Golden Gate Bridge would all have to squeeze in to a single resistor. This is just like a circuit with a single resistor in it. All the charges have to squeeze through that resistor. Well, boy, if this is silly, this is downright dumb. The Golden Gate Bridge is not going to have a lane of traffic with 3 different toll booths. You'd have to slow down for each one. That's crazy. That would correspond to a resistor or a circuit that looked like this. 1, 2, 3. Okay? And here, the current, the traffic, would slow down. It would scream to a halt. What we see on bridges is that you have multiple lanes. This far diagram is the same as this one. Don't think of it as I'm adding 3 resistors. Think of it as adding 3 lanes for that current to travel through. So now the cars can split up. They can flow through this one, they can flow through the middle one, they can flow through the one on the right. Adding toll booths in parallel increases the traffic flow on the bridge. Likewise, increasing the number of parallel branches increases the paths of those electrons. So the current actually goes up. Not intuitive if you're thinking about it in terms of resistors, but think about it in terms of parallel branches, additional paths for those electrons to travel. That was a bad diagram. Anyway, those are the basics between parallel branches. Thanks for listening.